What we are saying about the 7 Epsilon, why it is needed and why the need has arisen to make the progress in that direction, the new thinking has come into the practice, and why it is so important to us and why it is needful to us. That's what I will make attempt to present to you. So the mood will be set for the day. Zero defect manufacturing. Let us understand what is zero defect manufacturing. The zero defect manufacturing process, almost everybody of us wishes to have. Advent of automation and development in software has made it possible for the same. This certainly will be elaborated in the next slide. The domain knowledge of technology is indispensable, because knowledge is a thing which is growing every day, and we are certainly the inventions are taking place in every process and technology and the metallurgy everywhere. So the domain knowledge is indispensable, and in practice we see that zero defect manufacturing is a two-step process. First step is reducing rejection from 15-20% to 4-5%. That is somewhat easy and comfortable to all of us. With our domain knowledge, with our regular practices, when you look at the process, with our sixth sense, with our practices, with discussions with the colleagues, we make the efforts and we come down to 4-5%. But the real crux of the matter lies in the second step, that is reduce the defects from 4-5% to 0%. That's where the 7 Epsilon thinking comes in picture. Now when we analyze that, when we assess the importance, now let us define what is zero defect. To my knowledge, with my definition, it goes, the zero defect casting, a total sound, clean, neat and totally reliable cast component as desired for the application. I think this will be a most acceptable definition for that zero defect casting by the foundryman and by the customer. And then once we define this, let us understand why it is at most important to us. Let us see what are the financial implications of it. We know that we always take the pride that we are the second largest manufacturer of castings in the world, and we produce more than 7 million tons. When we say consider the rejection of around 5%, which is a moderate in our inner minds, we have to tally whether the figure is true or not. But say then we have the rejections of 3.5 lakh tons plus. And you see the normal CI casting cost, the average cost, right from say the normal say sanitary fittings to the engineering castings, you say it will come to the 55 rupees a kg, and total revenue loss is 19-20 crores, and all the calculations we are aware of it. We just look at the red letters, that is 1075 crores is a net loss to the foundry industry by the rejections. And if you save 1% of rejection, you are going to save 215 crores. This is the lowest figure. If you add some precious metals, the figure will go very high. So you can understand the cost of 1% rejection to the nation. Moreover, the cost, there are some other issues. The recent study has discovered that 1 ton of casting approximately produces 1 ton of CO2 emission and half ton of landfill waste. The landfill waste also produces the methane, which is 32 times hazardous to the CO2. So this is, as Dr. Agashi has said, I was associated with Terry for some of the projects. So in the study, we have come out with these figures. And then, so this is the environmental impact, and for no reason by producing the rejects, we also for no reason produce the greenhouse gases. So that is also a thing what we should understand. And other important effects. The sustainable growth is obstructed. Certainly, whatever we plan that, okay, this year we are going to make this, and then that gets obstructed. The important aspect of zero defect casting is the production is safety, because now the advent of automotive industry in India, almost all global manufacturers are here. We all are catering to them, and that is directly connected. Any failure is directly connected to the safety of human life. So that is also an important factor we have to understand. And the last one is absolutely important, that loss of good customers for appreciate the value of castings. We always do the ABC analysis in our product mix, and we try to see that who is the best customer and how we can get more orders from that customer. And if the culture is not known to the customer, if we miss that thing, then certainly we lose the good customers. So this is also most important thing. So rejection per se, we should not look at only one angle, but there are so many angles we have to think why to reduce the rejection is important to us. You see, when we think of the rejections, we have to think a total chain, because we know that we make the casting with so many sub-processes. And what they involve, it starts from methoding, then molding, core making, melting, pouring, and the last is energy. Energy is a catalyst, because without energy, we cannot perform anything of it. So though energy is directly not a process per se, but at the same time it is an important catalyst for that, and which is around 15% of our total energy of our total balance sheet. So that's also important. And then every methoding process has got the correlations with each other, and ultimately we get the good casting. Once we define what are the processes, and we certainly we need to optimize these processes to make it more economical and more quality cautious way. So what we have to remember when we think of process optimization, there is a better productivity, that is the important thing, at the lower cost and the better quality. This is the target for process optimization we have to think of. What is the gamut of all this thing? It is the human expertise, indispensable, certainly we need it. We have to reduce the scrap generation. What we need important is in-process data, and we have to check the process capabilities. When we look at the in-process data, we understand the limitations of the process capabilities, and we have to look at it. And then certainly we have the interaction of among 5 M's. The 3 M's is normally we know man, money, machinery, and all. The 2 important are measurements and methods. I mean, those are the things normally get ignored. So those are the things what rather empathetically I will like you to remember these 2 next M's, the methods and measurements. When we understand this, then we look at the details of the process. Then what does it contain? It contains so many the process parameters. The process for every process has got different process parameters. Whatever we have seen the process as such. Like this is the elaborated picture. Here we have the process parameters for everything. Mold making, you see we have got the mold hardness. Then there are so many mold parameters. If you the handout what has been given to you, it has enlisted around 20-25 process only in a mold making. Normally what we measure is, say, we measure the moisture, we measure the alloy, we measure the dead clay, active clay, compressive strain, GCS, compactability, permeability, all these kind of tests we take for the sand measurements. But these are the few parameters what we try to maintain and manage to get ultimately zero defect casting. Similarly, we look at the metal chemistry. We have got normally the basic for the cast iron, because I'm basically a cast iron man, so I just start with that. So the carbon equivalent is the most important factor. Similarly, it gets followed with the alloy additions like manganese, chromium, nickel, moly, whatever we need to get the quality, and phosphorus, sulfur, of course, those are inevitable to look at. So these are the metal chemistry parameters. And then core making. We know, suppose if you are using any shell resin cores or something, we know what is the resin contents, and we also need to check what are the hot strengths and other strengths and core hardness for the cores. And when we come to the next process, that is metal temperature and treatment, we also need to have several parameters like that. What should be the tapping temperature? What should be the pouring temperature? What should be the pouring time? And what not. I mean, these are the kind of parameters we need to measure. Then process methoding changes. We always think that, okay, we decide some method maybe with the simulation package, but at the same time, after having a couple of trials, we think that, okay, we may have to change a little bit in that, we may have to tweak with that. And then we really don't know whether this change in the methoding has helped us or not helped us. But so the methoding is also an important thing what we need to look at. And there also we make the changes. And the shift and operators, this is what I will like to get. These are the discrete parameters we normally don't consider when we look at our data sheets, process data sheets. We normally ignore to look at, but we observe, we discuss in the meetings or Kaizen board. We discuss that, okay, at a specific, suppose you have got the 3 furnaces and you are pouring the same casting day in and day out. You take from one furnace, the metal is taken from one furnace. Everything remains same, but the results are different than the other furnace. You really don't know why it is happening, but it happens. Something it also happens that some Rama is there at the core setting station, and the same process, same thing, same jigs, same fixtures he will use, same way he will do. If somebody else is there at the station, you get the different kind of reactions. You have the, at a particular method, everything is set, everything is observed very, very precisely. In spite of it, you find there are the differences in the reject levels at the first shift and the second shift. These are the discrete parameters. Normally we discuss, we leave it like that, we just guess something and leave it like that. But these are also important parameters in our entire process when we look at it. Then the equipment, as I said, the equipment also, I told you about the furnaces. So similarly, that goes valid for every kind of equipment what we make. And so, if you consider all these processes and you consider the parameters, total process parameters, they go as high as plus 110, which normally are known to me. So what we do with these process parameters? Say this is, we record the process data. Do we really make efforts to understand the process data? We really analyze the process data with respect to the casting production at the instance. That is, the last words are very important to us, because we ought to know at what specific time, at what specific job, at what specific batch the process parameters were existing. What was the traceability? When I produced this batch of castings, when I produced these 100 castings, what are the process parameters? What was my compactability? What was my pouring temperature? What method I was using? What size of filter I was using? And in how many seconds my pourer has poured that casting? So we must know that thing at that instance. Normally the logs are maintained, they're filed, and then okay, we don't know exactly what was happened at which batch. But these are the things the process data, when we look at the process data, these things carry utmost importance for that. And what the utmost importance is, I think Dr. Ransing is here. That is the very reason we have invited Dr. Ransing to tell us. What is the challenge ultimately? Each observation gives a different process parameters, as I explained you. Every observation shows different results. As I say, you have managed the spectrum of the process in your given limits with your domain expertise, what are the limits you have set. But at the same time, the results are different. So naturally, we measure them in the data and we log them. But we have to understand that there is a relationship between process parameters and the respective results. I'll just give you a simple example. So suppose we know the mold cavity, the volume is fixed. We have decided the methoding for that. We know in the first 10% of the time your mold must be full, you must be able to see the molten metal from the top of the gate. And then you see that you have set that process and you have decided that you are going to pour it at 1316 degrees temperature. That's fine. But sometimes there's always a range. So what happens? Sometimes you find the rejects and you decide with your own domain knowledge, with your experience, and with the time constraints. Okay, today I am pouring it at 1360. No, I am getting some rejections. I will make it to 1410. Fine. The 1410, have you considered, when you have thought of the 1410, have you considered that do you need to make any change in the methoding? Because what is the volume? Ultimately, what you are going to have? What kind of volume what you are going to get of the gas? Have you checked what should be the proportion of the venting you have provided? Permeability apart, you should know. The moment you change this, you should think of the venting what you have provided. Whether will it be enough for that? Or so this is the example. So what I'm trying to explain you what is the relationship. There is always a relationship between all the parameters. At the same time, when you think of it, you also think of the sand parameters. One change in any of a process, of any different process that is interlinked with every parameter. Maybe a change in moisture may lead to the change in compactability. Maybe your compressive strength changes. Everything changes. Then you have to look at the methoding. You have to relook at your filter size, what you are keeping. So all are interlinked parameters, and then they make the effect. Suppose if you consider, say we have innovated here 110 parameters. Say in normal life or day-to-day life, if we are managing with 20-25 parameters, and then you are producing a casting, say suppose gearbox oscillator. So you see you have got 30-40 times you have made the batches of it, and you have the different relationships and different observations and all these things. But the results are different every time. Though the process parameters, you are within the process limit, but at the same time there is a difference in that thing. You may be at the higher end or the lower end or something like that. And the results are different. You are 90-95% you are online, but 5-7% you are missing something. Then how to correlate it? Then what are the needs? The need to correct the process parameter for the desired results. That is the need what we have to address. The second need to know exact relationship between set of parameters and the results. That is there, hidden inside of your process data. That is the greatest thing what we need. And then the last And very important is need to know optimal setting for desired results. The optimal settings of your entire process, set of process parameters that you need to know, so you can take care of your rejections, you can reduce that and you can tend to zero. Gentlemen, everything in the part is absolutely logical. When you want to go from 5% to 0, it's not necessary that you have to jump from 5% to 0. You can go from 5, 4, 3, 2. If you jump, you may land in some accident. So think logically, do logically, and how to do that, how to make this optimal setting, how to get the results, and how to satisfy our needs. That's where exactly the new philosophy of this 7 Epsilon comes in picture, and that is the reason why Dr. Ransingh is here. So, gentlemen, let us understand the 7 Epsilon concept for the purpose from Dr. Rajesh Ransingh.